In this presentation, we will have a laboratory session. We're going to look at a cantilever beam with a tip load that oscillates at varying frequency. This is really what's called a frequency response problem. The cantilever beam is physically the same one that was studied earlier to find its normal modes. Later, in another lecture, we will re-look at this case using a so-called modal methods, where the base vectors in the problem are taken to be the modes of the undamped system. A more precise name for what we're doing then in this lecture is to call it a direct solution for frequency response. I start with a physical statement of the problem, and then I separate out the physical modeling from the finite element modeling, which I like to do. We look at the Nastran data set, look at the results, and then I do the problem again with several values of structural damping. The cantilever beam that we study is slender. It's 30 times longer than it is deep. We'll use a coordinate system at the left end, x along the axis, and z vertical. The force is vertical, therefore the linear system will oscillate in the xz plane. The cross-section was symmetric and solid, so there won't be any unusual coupling between this vertical motion and other motions in the problem. Our solution is going to run as shown here, where we drive the oscillating force through the first natural frequency of the body and show this peak near the first frequency. Interested viewers can easily extend the frequency range on up to capture the behavior near the second and third natural frequencies. Physical modeling that we do, we're going to use the small deflection behavior of the Euler-Bernoulli beam, which has plane sections remaining plane. We're going to assume linear elastic material behavior and planar motion in the xz plane. We'll be neglecting torsional vibration and axial vibration and out-of-plane vibration. That is, motion in the xy plane. We'll only check frequencies every 2 hertz. Nowadays, with fast workstations, people can do a much finer frequency resolution than that if they wish. Our finite element modeling will again be a simple 2-bar element model. We'll constrain the root of the beam, making it a cantilever beam with the tip free. We'll constrain all of the unneeded degrees of freedom at the outboard nodes, namely the axial, torsional, and out-of-plane bending degrees of freedom, 1, 2, 4, and 6. That will again leave us these 4 active degrees of freedom during the solution. And our oscillating force acts directly on what I'm calling U5 here. These have been renumbered in a local sort of a way just to show the total number of degrees of freedom here. In a frequency response problem, one of the more serious tasks is to identify the details about the oscillating load. Mathematically, our tip force has this form of 1,000 newtons oscillating at a frequency characterized by this capital omega. There's a very general capability within MSc Nastran to model such loads, and they allow you to either use a rectangular Cartesian approach in complex variables typified by these constants, or a polar version typified by these constants and phase lags with this amplitude. We're going to choose to use the form with the amplitude of 1,000 newtons, and then set the imaginary part to be 0 here, and to set the these various phases in here to be 0, and not to have any offset time scale. It's helpful to me to diagram the relation of some of the data entries in MSc Nastran. When you have a frequency response case, we call for a dynamic load here up in the case control, and there is also a related frequency card. Both of those point down to bulk data entries below. We have this RLOAD1 card that allows us to enter those 5 parameters that generally characterize a harmonic load. The frequency has a set of discrete frequencies called out on the Freq1 card, and each one of those solutions then is equivalent to a static finite element solution. So you can see that if you ask for a lot of frequencies, then you can, in principle, have an expensive run. Now let's look at the exact data cards that we're going to use. First of all, we have the ID with as many as 8 characters in each of 2 words separated by a comma, starting with a alphabetical character. Time in minutes, we're going to use Sol 108, direct frequency response. This is in contrast to a modal frequency response. Case control commands, we have a title, and I'm going to call this a subcase 1 just for a general training tool. There's only one subcase, so it's a little bit superfluous. Then we have a subtitle. We're going to ask for all the displacements. I will continue with the case control commands. Here's our dynamic load, which is a flag pointing below. Here's our frequency flag that also points below. And here are plot instructions. And in this case, we're going to look at the shape of the deformed beam. Now, the beam will go through some sort of a deformation pattern, and then we will be oscillating back and forth between those 2 extremes. And we'll just plot 1/2 of that cycle at a reference time. We'll look into the minus y-axis using x horizontal to the right and z vertical up. And we'll plot and label the elements and nodes and look at deformations as a function of frequency. Now, the bulk data entries involve the same 3 grid points that we had previously. Here we show the remainder of the bulk data entries. The connectivities here are standard. They do involve a vector which points out the 1 plane. The 2 plane is taken perpendicular to that, and it's actually the I2 here, the smaller of the 2 moments of inertia, that control the flexure of the beam bending in the 2 plane. Our material here is standard for steel with the density. We will use coupled mass again as we did in the normal mode problem. Here's our dynamic loading as referenced from above in the case control. It has a magnitude 11, which points to a D area card, and that gives a node and a direction of the force, and then the magnitude of the force of 1,000. The 27 points to a scale factor, which could be a frequency changing magnitude of force change, and a graph is set up with the coordinates 2 and 1 here showing the starting point, and then 18 and 1 showing the ending point. So we have a constant scale factor of unity over the frequency range. Then the Freq 1 card here tells about the specific points at which the frequency response will be calculated, starting at 2 Hertz in increments of 2 Hertz and 8 more times. These data were entered into a workstation on my desk and then networked to a Sun workstation at the Michigan Computer Aided Engineering Network, where it was run on MSC Nastran. In discussing our results, let me first review the natural frequencies and mode shapes for our beam. We already found from an earlier lab that the fundamental mode was 9.2 Hertz, and the mode shape looked like this. Second mode 57 Hertz with this mode shape, and third 161 with this mode shape. Now, as you shake this body at a very low frequency, you will probably get something close to the static deflection shape of a beam with a tip load. Now, that's a shape that I'm not showing here. It would be a cubic curve, though. The exact solution would be a cubic. Then when you come through the first mode, you'll get this shape, which is actually known to be a transcendental function when you solve for it exactly. Hyperbolic functions, sines, cosines, and so on. And then these second and third modes are also transcendental when you get exact solutions. So that we know that when you excite this beam with frequency starting up at 0, you're going to get a response that's almost like the static shape. If it were a very low frequency, people might call that a quasi-static response. Then at these other frequencies, when your exciting force is near a natural frequency, that shape will dominate, in fact. So you can expect it to look like this figure when we plot the displacement amplitudes of our forced beam between 0 and 20 Hertz. Let me show you the actual output from our run. Here is the sorted data echo. A nice way to look at the data when you want to get it in a universal form that other people can easily understand. From the tabular results, let me show you a couple points that bracket the natural frequency. Here we have the frequency of 8 Hertz, and you can see the mid-node translation in the z direction as 4.5 millimeters, and then outboard at the tip we have 13 millimeters. That's when you're slightly below the natural frequency. When you get above the natural frequency, then you find that the displacements are out of phase 180 degrees with the time reference for the force. So in effect, the force is moving up and the beam is moving down. This reminds me a bit of the case with a paddle ball on a string on a board, where you see children playing with such a game, and the board and the ball move in opposite directions, so you're out of phase when you get up above the first natural frequency. This one's slightly higher. There's no meaning to that other than that you're a little bit closer to the natural frequency, but it's the sign change here that's important compared with the 8 Hertz. Now let's look at the shape of the beam vibration as we raise frequency. We'll show the lower frequencies here, and at the lower end you would be getting a quasi-static response that would probably come close to the static deflection of the beam under a static load. I probably won't sketch this very well, but let me try to do a little bit of a... And so our beam is oscillating, of course, between those upper and lower envelopes. At 4, 6, and 8 Hertz, you are probably becoming more and more similar to the first natural mode shape. But then as you reach 10 hertz, you get the surprising sudden 180 degree phase shift. But that makes sense, of course, as people who look at these systems know. And here we see the frequency response curve for the magnitude of the motion at the tip. I haven't normalized that motion by a static deflection. You can see that that static deflection is about 3.5 millimeters, half amplitude. And in our particular curve, we follow the response to a point rather close to resonance, and then follow on the other side as well. Because we're plotting absolute value, the 180 degrees phase shift that comes up through the natural frequency is not shown, of course, here as a sign change in the amplitude, but rather as a phase change on the phase plot for frequency response. The phase angle as a function of frequency is very interesting. There's a 180 degree phase shift. I've arbitrarily called this original phase to be 360 degrees rather than 0, so that then the resultant drop brings us down to 180 degrees. Now, when there's zero damping, this happens very quickly, and I draw that as a vertical line. So far we've been studying a beam with no damping. Now it's important to add a little bit of damping to get a realistic problem, because the undamped beam would go to infinite amplitude when you resonate it. We know every physical structure has some damping, so we'll start adding a little bit. In structural damping, we can add either an element by element damping, shown here to the right, or we can add a system damping here at the left. If you want the system damping, you can enter that G parameter on a param entry. We will be using structural damping in our next run, but let's talk about viscous damping as well. There are three ways that this can be entered into the Nastran data set. You can use viscous elements called VISC, and these are rod-like, and they're illustrated over here. You can use a CDAMP1 card or a DMIG card to enter a damping matrix. You notice I'm using the old-fashioned word card here, and I'm more and more trying to replace that with the word entry, which is the modern version since we don't use cards. But it's very hard to make an old dog learn new tricks, I guess. Okay, so let's do this rerun and do it with damping now. And I'll take a structural damping coefficient globally of either 5/100ths or 1/10. And that can easily be done just by adding a parameter card down in the bulk data. Another thing I'm going to do is make XY frequency response plots. And it takes a few tries to get those to work in Nastran, but that's simple enough to do. And once you've got it, you've got it. Here are the data that I'll use for our improved run, including damping and frequency response plots. I show in red the cards that are added, and here is the G comment on the subtitle card. Here's a request for the frequency response curves. To get those in the standard form, you have to do it in the polar form, where you use the word phase in displacements. If you don't do that, things don't work well. And then we use the plotter here, and on these XY plots of displacement response, out here you have at node 3 the translation in the 3 direction, and we're using the magnitude there. And the next plot you make at degree of freedom 3, we're doing phase. So it's magnitude and phase we're getting when we use this word phase up here in the displacement entry. To account for damping, we make only a modest change in the bulk data entry. at this level for a parameter card with G set in our first run to 0.05. Our tabular results can be interrogated here to see what the effect of the damping has done. When we're just below the natural frequency, that is when we're at 8 Hertz, we find this result where we're getting 348 degrees rather than the full 360. When we're above the frequency, we see rather than getting the 180, we're at 196. So this has softened that sudden jump into more of a gradual jump, and we'll see that in a plot in a minute. I'm ready now to plot the combined results from runs with no damping, 0.05 damping, and 0.10 damping. Interestingly, though, these are all relatively small, and you can see that although there are substantial differences, they tend to lie pretty close to each other on a line that's almost vertical. So it would be fun to redo this with a few more data points and really see where we come. In fact, it would be fun to see if, for instance, on G equals 0.1, whether you would peak out at 10 times this static displacement. Because remember, the magnitude enhancement for dynamics, call it the dynamic magnification factor, is 1 over G. Therefore, the maximum displacement ought to be 10 times the static displacement. Now let's look at the phase angle versus frequency. Here we have the 3 damping cases again, and you can see the last one, for instance, with G of 0.1, has started to definitely soften. And the higher the damping, then the more that this curve would come more smoothly down. It would be fun to put some bigger numbers here, so I'll leave that up to the viewer to perhaps go up to G of 0.5 and see what that does in this problem. Certainly smooth out this phase jump. I pondered over these results some and realized that there's a lot of interest in industry about the shape in which a vibrating structure moves when it's forced near a natural frequency. And I wondered if there was some way to quantify how this structure approaches the mode shape you'd expect when you resonate it. Because when you're off resonance, what happens? Does it suddenly lurch into some other exotic shape and do something completely off the wall? No, the answer is it rather smoothly changes its character as it passes through the resonant point, and right at resonance achieves, with the structural damping anyway, exactly the same shape as the eigenvector for the problem, which is the undamped mode shape. So in this figure, what I've done is to plot the ratio of U3 to U5. And this gives you some idea of the shape of the structure. Now I admit that's only one measure. You could have measured a bunch of others as well to really get the shape. But I put that ratio on the ordinate here, the vertical axis, and then on the abscissa I've got the frequency. And where I've put a vertical green line is the natural frequency, and that's also the resonant frequency with structural damping. And I looked at the eigenvector for the undamped problem and found that that ratio should be exactly this number here, 3395. And lo and behold, that's what you get when you interpolate to that frequency from our rather smoothly changing curve. So I thought, gee, this is great. This shows how a system, when you excite it and pass through the true natural frequency, you recover the mode shape. as a forced vibration. Remember, the true definition of a mode shape is unforced, just freely vibrating. And this is an undamped case. In principle, this would be an infinite amplitude at that point, so it might actually be hard to carry out this test by taking very small frequency increments, because as you approach that natural frequency, you would get an infinite result. So it's as if you could see a curve that came up, and then there would be a slight break where you couldn't get the end to go on. But that point exactly reflects the normal mode of the undamped structure. So that's kind of amazing and interesting. I repeated this same process in the neighborhood of the second natural frequency and resonant point. Those are identical. And when I did that, I found the same thing happens. And I plotted not only the undamped, but also the damped case, and that didn't change things. So isn't this interesting? We really do recover the shape of the eigenvector, which is the second normal mode, when you force the beam at that frequency. And when you're in the neighborhood of that frequency, you get a shape that's in the neighborhood of that normal mode. So we really have shown then that as you oscillate a system, that as you pass through resonance, you really are picking up the free vibration character of that system. I think this further reinforces the idea of using the normal modes and frequencies of a structure as sort of a way to characterize the structure to other people. And it can now be well inferred that in the forced response problem, you indeed get the shape of the eigenvectors when the frequency is in that neighborhood. So I think that answers one question that I had always had, and I had never seen this shown explicitly like this. In this lecture, we will consider modal solution methods. Up until now, we have primarily talked about physical coordinates such as displacement vectors. Now we're going to change our view and use a different kind of vector basis to describe the displacements of the body. These are the eigenvectors themselves of a freely vibrating system without damping and without external force. So this set of eigenvectors forms a convenient vector basis. The nice thing about it, like a Fourier series, is that the longer wavelengths components are more important, and these correspond to lower frequencies for us. So if a person can carry a certain number of the eigenvectors as base vectors, you can concentrate on the smaller frequency end of the spectrum where the wavelengths are the longest. Vehicle industries such as automotive and shipbuilding, aircraft, often use modal methods because the structures are so large that they can't really contend with all the physical degrees of freedom. A driving factor here is that the finite element model is usually so large due to the geometric requirements to point out all the holes and bends and curves in the surface that by the time you get to a dynamic solution, you really have too much fine detail in the problem. So using modal methods is a way to take a look at the more important forms of motion of the structure, namely the lower modes. I'll give a little bit of an overview to start. Then we'll discuss the use of eigenvectors as base vectors. We start out considering the academic case where you would carry all of the eigenvectors as degrees of freedom. But then later we soon learn how to truncate and reduce that set to a manageable set of vectors. For instance, in an automobile study, a study might consider the first 50 modes in a vehicle structure that might have hundreds of thousands or even 1,000,000 degrees of freedom. We'll check the damping and how that enters. Then we will look at a example problem for modal frequency response. This is a good application, and we'll repeat our lab problem where we had done this previously with direct frequency response, and that means using the physical coordinates. We'll just mention modal transient response because we're not ready to really do that type of work yet, and then I do some problems in the problem session. Normal modes are used to solve a number of practical response problems. Here's a list of the solvers within Nastran, both for direct solution and modal solutions. The three that we are concerned with today are these bottom modal methods. But to start off, let's mention that we do normal mode studies to get the base vectors. That's the solver 103 in Nastran, and we had a lab on that. Then you can do direct frequency response. We did that in our lab number 6. You can do direct transient response, and that will be done in our lab number 7. We haven't done that one yet. Complex eigenvalues can be found directly. I only look at this once back in the lecture on robotics, where we look at stability of a robotic system. Anyway, that's a solver 107 in Nastran. But what we're interested in today is modal frequency response and solver 111, and that is our current lecture. We won't get into modal complex eigenvalues nor modal transient response, but I think you'll get the basic idea out of looking at modal frequency response. Let's review the normal mode process, because those normal modes are our base vectors, as if in a Fourier analysis. The undamped system equations of motion are shown here. These are ordinary differential equations. They're second order. This is a matrix form. We know that the mass matrix M and the stiffness K need to have certain properties in order to ensure correct solutions. For instance, we want the mass matrix typically to be real and positive definite and symmetric. The stiffness matrix normally is a real symmetric matrix and positive semi-definite. If there are some rigid body modes possible, then those correspond to zero frequencies, and that can happen. So K might be semi-definite. The solutions that we've identified, we use these special symbols for. We have the frequencies omega and then the corresponding mode shape phi. I'll use a subscript to show which of the normal modes it is that you're speaking of. And here I've listed 3 of them, but in an n-dimensional system you will have n sets of eigenvectors and frequencies. So it's clear that there's just a very enormous amount of information here in the normal modes. If you had a 30,000 degree of freedom system, you would in principle have 30,000 eigenvectors. According to Rayleigh and his earlier thoughts, at least half of those are bogus because the system can't accurately describe the top half of those. But the lower modes are generally fairly important physically and mathematically. What we do then is form a transformation matrix where we stack up the lower modes. So these are the phi vectors shown here, and I show 1 up to some number n. And if you carried all of these, they would form a complete set, if n indeed is the size of the set of equations. Normally, though, we will truncate and take only a subset of these vectors. But there are some mathematical theorems about these eigenvectors. They are orthogonal. They so-called span the space, which means that they're a complete set of vectors equivalent to the use of Fourier analysis, say, in a time history like used by the electrical engineers to analyze voltages and current. So these will be our modes that we will use to represent the total problem. We'll use these base vectors now as a way to represent the entire problem. The physical nodal displacement vector is transformed by using the eigenvectors then as these base vectors. The C quantities are generalized coordinates or participation coefficients. I'm showing this set of coordinates going up to lowercase n, and we will consider that to be the size of the original problem, say 30,000 equations. So this is meant to be a full transformation and not truncated. And you find that when you have a set of vectors in column form as shown here, then the participation factors or these generalized coordinates are a post-multiplying vector on the back here. Then you make that substitution into the original physical equation of motion where the acceleration, velocity, and displacement vectors are expanded in terms of these normal modes as shown below. And this is a set of n equations and n unknowns. You could solve this as it stands, but there are some good, strong reasons for converting this into more of an energy notation rather than a force notation. Currently you have a set of equations which in a structural theory alternately describe translations and rotations. And this is often not numerically well posed. The accuracy can suffer. So it's better to continue, as we will in the next slide, and use a Galerkin type approach where we convert each of the equations into an energy balance, and then you get a better numerical solution. This energy approach seems to be called Galerkin's approach by many authors. I'm not certain why, except that in the integral forms of this, Galerkin did do this early, where he posed error